it's not just like the other questions where you actually just simply apply the formula and then you will forget about all these questions, okay? But question 8 has some kind of interesting context that I believe is very useful to know, okay? Especially when you try to use statistics on real data analysis, okay? So, okay, so let's look at the context of the question, right? So it says a group of veterinarians wants to test a new vaccine for Lyme disease. So this Lyme disease is some kind of disease transmitted by ticks, okay, that carry this some kind of bacteria. I don't know, like you know Justin Bieber, right? That singer, okay. So he claims to have Lyme's disease. All right, he claims that he was diagnosed with Lyme's disease. Okay, so apparently this is quite common in North America, where people usually they live with their pets. Okay, and if their pets have ticks, and then they usually they might actually sleep with their pets. Okay, so then if their pets actually are not clean and they have ticks with them, then they may actually get bitten by the ticks and then get this disease, okay? So it says in an area that has a high incidence of Lyme's disease, 100 dogs are randomly selected to receive the vaccine, right? So over a 12-month period, these dogs are periodically examined by vets for Lyme disease, okay? Then at the end of 12 months, 10 of these dogs are diagnosed with the disease. During the same 12-month period, 18% of the unvaccinated dogs in the area have been found to have Lyme disease, okay? Let P be the proportion of all potential vaccinated dogs, okay, and so on. Then find a 95% confidence interval for P, and so on and so forth, right? Now, for most students, right, when they look at this question, basically they will just start doing some calculations, okay? And doing the calculation is actually trivial because all the information there seems to be information around, right? Like for example, you want the 95% CI for P. Most students would say like the P hat, right? They will find the P hat first, which is from there. They'll say the P hat is 0.18. Okay. They'll say that the P hat is 0.18. So then they will proceed to do P hat plus minus 1.96 square root of P hat 1 minus P hat over N, right? In this case, sorry, no, your P hat is actually 10 out of 100. Okay, sorry. So then your N is 100, okay? Right, so then they can find this, and then P be the proportion of all potential vaccinated dogs who would have contracted. Okay, so then this value, and then you have this value, right? So this value will be, if you quickly calculate it, is 0.1 plus minus 1.96, 0.1, 0.9 over 100, okay? So this is about, can somebody calculate this? So it's 0.1. If you do the calculation, it is 0.042 and 41 and 0.159. Okay, so then your 0.18 is not in this interval, right? So then it seems that you have some evidence to suggest that vaccination works, right? Because if you do vaccination, only 10% of the dogs end up with the disease. But if you don't do vaccination, then 18% of them get. So there seems to be a reduction of 8%. This reduction is meaningful because your 18% here, right? It seems the difference seems to be not explained by chance because it lies outside of your confidence interval. Okay, so but then is that all? So part C says give a brief critique, right? So how do you criticize this experiment? There's something wrong with this with the conclusion of this experiment. Actually, there's something wrong with the design of this experiment. Where's the problem? It seems okay, right? Looks like you have data, right? But then you have to watch very carefully how the data was collected. Okay, so where is the problem with the design? Anybody wants to give a try? Maybe I just draw out the design. The design here is like this. So this group of dogs, this have owner consent, right? These have no consent, okay? So then you then you give you randomly pick 100, okay, to vaccinate, and then you'll find that p hat is 0.1. So after that, this one there's no vaccination, so your p hat, this one is vaccination, this one is no vaccination, right? Then your p hat is 0.18, all right? So which indicates that the infection is actually more severe in the group that has got no vaccine. What is the problem with this design?
Wouldn't no vaccination be 1 minus the original P hat?
Sorry?
The one that we should use, the no vaccination, shouldn't it be compared directly with the one we choose, the 100 sample?
It's okay, it doesn't matter. This one is the infection rate. So if you use 1 minus is the non-infection rate. So you could either compare the infection rate or the non-infection rate. That's just they are equivalent because it's just looking at the other side. Okay. So we can just keep this. I want to focus on the problem with the design of this experiment. There's some problem here. Can you find it? Okay, so since we are about
the consent?
yeah.
The consent, because if we chose the no vaccination, should be the ones with owner consent as well.
Okay. And why is that?
Because we're comparing two different Because I'm not too certain as well, but that's what I see as a problem. Or maybe I'm wrong.
Okay, I think you are right there. Now you see, the problem here is you are comparing the group that you're comparing, right? They are actually confounded with owner consent. Okay. Now, owner consent means the owner whether they want to give consent or not, right? The problem is that once you have this, right? Basically, when you see that there's a difference, right? You are not sure whether it's due to the vaccination here, or is actually due to the consent status, right? Because some owners who don't consent, right? They maybe have some the way that they raise their dogs, right? Maybe a bit different. Maybe, for example, they are too busy. Okay, they're busy people and so on and so forth. So they don't take care of the dogs. All right. For all you know, maybe if they take care of the dogs properly, they shower them and all that, then there's no problem. But then since they might be too busy, so they don't give consent, they don't want to have anything to do with research, then of course the dogs will get, they might have a more likelihood to actually get infected, right? It's got nothing to do with the vaccination. Okay, so this is what we call confounding, right? You see, they don't have the same, so the comparison, right, are not equal for variables except the intervening variable, right? Except the intervention. You put an intervention which is vaccination and no vaccination, but actually the background variables should be actually the same, all right? So the dogs should actually only differ in whether they get vaccination or no vaccination. But in this case, they actually differ in terms of the consent, which can be associated with the background of the owner, right? So in this setting, right, what would be the best way to actually do this experiment? How should the comparison be done? So we know this is has confounding problem, right? So if you were to redesign this study, how would you redesign it?
By only taking those who give consent.
Okay, and then what do you do? So you basically, you ignore this group because there's nothing you can do with this group, okay? So you work with this group, and then, so then you basically, you randomize, right? You randomize, let's say 100 to vaccine, right? And then you randomize the other 100, let's say to, so vaccine and no vaccine, okay? So basically, then after that, you compare the p-hat here is 0.1, but this p-hat here, you have to find out, right? You don't find out the p-hat from this group. This p-hat here has no use because it's confounded with the consent status. But if you find out the p-hat from this group, right, where you didn't receive vaccination, then it will work, right? You compare these two, it will work because in this case, their background is the same, right? You don't have confounding in terms of background because both of them have owner consent. So people who give consent, their background are generally maybe more similar, right? Maybe they take care of the pets. They care more about the pets. Okay, so you eliminate that kind of confounding. So that would be a correct way to actually obtain the data rather than this one, right? So if you compare the data from this p-hat from here, which you already have, but then this p-hat you don't have because you didn't collect it, right? So this tells you how important it is to actually design your study. And actually the calculation is secondary. All these calculations that you see, right, they only work when the data has been collected in the proper way. Okay, so please, this is an important take-home message because too many times people, when they do statistics, they basically just throw in some numerical values into some formula and think that they have something. If you look at the context carefully, right, sometimes there's actually nothing there, okay? So this is the important message from this particular question, okay? Right. Okay. So I think we are just about time already. All right. So I hope you have learned something today. Okay. So later I'll post the video recording and pass you the link. Right. Okay. So thanks to everyone for listening.
Thank you, Doctor.
All right. So is everyone familiar with confidence intervals? The idea. Can somebody explain to me what a confidence interval is?
An interval where we can say that percentage confidence of that probability of occurring, or for some mean.
Okay, so in fact, actually, a confidence interval is actually quite it is quite an abstract concept. Let me see. Let me go to the whiteboard. Okay. So basically, it goes like this, right? So for example, if you have so this is the population distribution, right? So if you take a random sample, like for example, you take a random sample, you may get some values like this, right? So that may allow you to construct a sample mean, okay, for the first time, right? Okay. And then if you take, so this is the sample mean for the first time you do the experiment. The second time you do this experiment, you may get something like this. Of course, it will be different, right? Because you are randomly sampling. Maybe something like that, keeping the sample size the same, yeah? So then you will have another sample mean, right? Okay. So if you repeat this many times, you may actually get many times, right? So you may actually get many sample mean values, okay? All right. So these sample mean values, they can form a distribution, right? So in this case, if I overlap this distribution on sample mean, they will go something like this. They will get centered around the population mean, right, mu. Okay, so this is the distribution of your X bar, right? You have to imagine that you repeat this experiment many times, okay? And so, but this is, of course, you have to have some imagination of repeating it. But of course, you will only in practice, what you get is you only get this value, right? Okay. So what happens is that you want to find out some uncertainty about the sample, the estimate here, the X bar, right? So we would say, we would have some statement like this, 95% confidence interval for mu. Okay, you have some formula like this, X bar plus minus, in this case, if your sigma is known, yeah, and your population is normal, then you will have some formula like this. (1.96) sigma over square root of n, right? If sigma is unknown, then your X bar will be plus minus the critical value for the t distribution. Okay, so alpha over 2 n minus 1. So this is the degree of freedom. So this alpha is in this case your alpha is 0.05, right? So then you have the t, this is a critical value here. And then you have the sample standard deviation. You basically replace it with the estimate and divide by square root of n. You have some formula like this, okay? And you then give it a name called the 95% confidence interval, okay? But what it really means is the follow. Now, you can actually, for every sample, right, that you have, you can actually construct a, you can actually construct a confidence interval based on that, this formula, right? So basically, this is your estimate of mu, and this whole thing here is what you call the margin of error, okay? Margin of error. So it will be centered at x bar, and then it will have some length like this, okay? And obviously the length here is controlled by the sample size. If your sample size is large, the length will be short, right? Okay, so of course having a short length is better because then you don't have to consider so many possibilities, right? And in fact, this controls the amount of uncertainty, right? This makes sense because if the larger your sample size is, if your sample has been randomly taken, then there's more information, right? Now, for the first sample, if you construct the confidence interval, it may look like this. If you repeat the experiment, you may actually get the second time, it may actually look like this, right? Every time you do it, it will be slightly different from the previous one, right? So I'm just drawing out some examples here. Okay, they won't be exactly the same because it depends on the sample, right? So it depends on your X bar, right? So every time it will change. Now what happens is this, if you repeat this many times, okay, so suppose this is your correct value. This is your population value mu. In some cases, right, your confidence interval will actually fail to contain your mu. But each of them, they either contain mu or they don't contain mu. Okay? So like for example, if I give you a particular set of numbers, so this confidence interval either contains mu, in this case it does, or it does not, right? So you cannot say that a confidence interval is there's a certain probability that your mu falls inside that interval. It doesn't mean that, okay? Because whatever confidence interval you have constructed, it is only for one particular instance, okay? And it either contains or it does not contain. But you can imagine that it's more about a procedure. It's talking more about the properties of a procedure. So if you imagine that you repeat this experiment many times, like let's say 100 times, okay? Then on average, right, if you use a 95% confidence interval, on average, 95 out of 100 of this length, right? This length constructed using this formula will contain mu, okay? Right? So it's talking more about the properties of a procedure, okay? Rather than a specific statement about whether your mu actually falls inside that particular interval. So in this sense, it's actually quite an abstract entity, okay? It is not, it looks deceptively easy, but the real interpretation is slightly more abstract, okay? You have to understand it as talking about the property of a procedure, okay? But nonetheless, for any particular example here, like one particular instance here, the confidence interval will tell you something about how reliable is your estimate, all right? If, for example, if your width is very long compared to this one, okay, then usually you would not put too much faith in the estimate of your X bar, right? Compared to this one, okay? For example, if you have two confidence intervals of the same alpha level, then you would basically prefer this one rather than this one, okay? So this is actually, I just gave you some background explanation of what the confidence interval is, because basically if you just want to calculate it, it is very simple. Okay, you just replace the necessary algebra with the values. Okay, there's nothing complicated in that, right? But to try to have some meaning and understanding of these things is a different thing. Okay. So okay, so I given you some basics about this, right? Okay, so then let's go back to the tutorial question. Share. Right. Okay, so they basically, so over here, basically all the questions are talking about, they just giving you exercises on applying the confidence intervals, the formulas, all right? So which one do you want me to discuss? Which one do you think you have difficulty?
Maybe number 10,
Sorry, question?
the last one.
The last one? Any other? Okay, I'll just start with 10 first, all right? Since then the others can think about what questions you want to ask. Okay, so question 10 says, when calculating a confidence interval for the population mean mu with a known population standard deviation sigma, describe the effects of the following two changes on the confidence interval, okay? Doubling the sample size, quadrupling the sample size. Okay. Give two reasons why this relationship does not hold true if you are calculating a confidence interval for the population mean mu with an unknown population standard deviation. Okay, so let me go to the whiteboard. So one is doubling, the other is quadrupling, right? And in this case, you have a known population mean and variance. Okay. All right, so your 95% CI for mu, right? Actually, it's not 95%. It's just basically any anything. So we'll replace it with 1 minus alpha times 100% CI, okay? For mu, so it's given by x bar plus minus z alpha over 2, then sigma over square root of n, right? Okay, so this z is your critical value from the standard normal, okay? Table. All right, so you can find that in the normal tables, okay? Now, so one thing is, okay, so what happens if you double the sample size, right? What changes to a confidence interval? So usually we describe this with the length, right? So the length of the CI is the right end minus the, so you have, it's like this, right? So this is your x bar minus z alpha over 2 sigma. This part is a plus, right? Okay. So in your middle is your x bar, all right? So the length of this is the right-hand side here, subtract the left-hand side, okay? So you will end up having twice of z alpha over 2 sigma square root of n, okay? So that's very easy, right? You just double this. So the length is basically just twice of your margin of error, okay? All right, that's very simple algebra. Now, what happens if your n becomes 2n? So that means you replace, right? If your n becomes 2n twice, right? Then your length will basically just be, length of your CI will just be 2 of this over square root of 2n, right? Okay. So basically this will be 1 over square root of 2 times the length of CI, okay, for n. Okay. So basically it will basically what? Reduce by a factor of the length of the CI will reduce by a factor of 1 over square root of 2. Okay, is that clear? So basically you just need to change your n to whatever, right? Here it says doubling, so change to 2n. But then you express it in terms of the previous length, right? So this makes sense, right? If you double, it should reduce. The length should reduce, right? Because you have more samples. Then if you quadruple, means your n goes to 4n, right? So then your length of your CI will be just, again, the same thing, right? But this is 1 over 2, right? Of the length of CI for n. So it will reduce by a factor of 1 over 2, okay? So that means that if you have a confidence interval, right, of certain length, if you increase the sample size by 4 times, right, quadruple, then you will expect its length to actually decrease by half. Okay, right? So this is just basic algebra, right? And then it says why is it that this relationship does not hold when your sigma is unknown? Okay, let me clear this. Right now, when your sigma is unknown, right? How do you get the confidence interval? So when it's unknown, your confidence interval is you have to use the t distribution, right? So your critical value, instead of using the z, you have to use the t. It's alpha over 2. This is the degree of freedom. And this part here is the sample standard deviation over square root of n, right? So its length for n is twice of this thing, okay? Right? Now, suppose you double, right? What will happen? So what will happen when you double?
The degree of freedom changes dramatically.
Ah, okay, that's very interesting. So you go back to this one, yeah? Okay. When your n is 2n, right? So this will be 2t alpha over 2. But instead of n minus 1, you have 2n minus 1. So s over square root of 2n, right? So this thing, And this thing here, the critical values are not the same, right? This is not equal to this, right? So you can't write some, so there's nothing you can do. So at most what you can write is something like this. We take out the factor of 2, and this will be T alpha over 2, 2n minus 1, right? Then this part here you can keep as it is, but you have to multiply with something like this. All right. Okay. Actually, I should write it here. This one should be here. Let me just do this. So it should be okay. Maybe I don't have to write like this. So you can just simply say that your critical value is not the same, right? So you can't actually express this as you cannot write this as some constant of the length of n. Okay, since your critical value changes because your sample size changes. Okay, it's the same with the quadruple. Quadruple simply means you change it to 4n, right? Okay, it's just a simple thing like this. You just need to argue it like that. Okay.
Thank you, sir.
Okay, then I have a request for question 9. Okay, so question 9 is
for question 9, is it because they give all Senator voting, so meaning it's the population already?
yeah, right. That's correct. Okay, so this question 9 is telling you that you got to understand the context of the problem, right? And not just blindly apply some formula. You see, this is very common with students. If you do not actually understand something, right, you will actually just perform whatever things that you think you are doing that gives you something, right? It's superficial. This is human psychology. If you don't understand something, right, they basically will just copy something that is there and totally ignore its context. So here you see, it's trying to tell you something like that, okay? You see, it says the Senate has just passed a bill by a vote of 55 to 45 with all 100 senators voting. This is some US kind of situation, okay? It's theirs. So then basically it says, oh, we can actually calculate a confidence interval about P, and then you have n equals to such and such, and so on, and then gives a formula, and then comes up with something that looks credible, okay? But if you really understand the problem, right, you know that this is total rubbish, okay? Because first thing, this is basically, there's no sampling involved, right? This is basically a very straightforward situation. You only have 100, the population is just 100. It's all that 100 senators. You're not taking a random sample of 100 senators from like a large pool of senators. You don't have that situation, okay? Whereas the context which allows you to actually use the this approach, the confidence interval approach, is that you have a sampling situation, okay? You're basically just taking a subset of your population, and then you want to quantify the uncertainty that's associated with your estimate, okay? In this case, there's no uncertainty because your population, you have completely enumerated it, right? So it's just an situation like this, okay? So it doesn't make sense because the answer is very simple. Doesn't make sense because the 100 senators constitute the population. So there's no sampling uncertainty, okay? This is a conceptual problem, right? Okay, so take note of that, yeah? When you try to use statistical results, you need to know the context, okay? It's a very common problem. If you ask this problem to 10 students, right, almost you might get 8 of them just start applying the formula, and this is a very common problem, okay? Because it requires some kind of sensitivity to the distinction between populations and samples, which you actually learn at the beginning, but most of the time after students learn that concept, right, they sort of like just put it aside and forget to turn it on. You have to turn that concept on all the time. So how about some other questions? Question 6. Okay, a random sample of 20 managers was taken, and they were asked whether or not they usually take work home. Okay, so you got yes or no, right? So make a 99% confidence interval for the percentage of all managers who take work home, right? So basically you have to count how many of them are yes, right? So that would give you okay, so okay, so you have you can count how many are yes, right? So a p hat is the number of yes divided by 20, right? Okay, so then basically you just take p hat plus minus z alpha. So what is your alpha here? 0.01, right? Okay, so 0.01 over 2 times square root of p hat 1 minus p hat over n. Okay, so that will be your 99% confidence interval. So you just need to plug in all these things, right? So I leave that to you, yeah? Okay, you already know your p hat, which is from the counting. And this one you can find from the table, right? So this is basically you'll find z 0.005, okay? Right, so the Zoom is going to stop me because it's only 40 minutes. So I'm going to end and then send another link to you again, okay? All right, so I'm going to continue for another 15 minutes, but I need another session, okay?